Okay, so we have been talking about clipping, right. So, the idea there was that we have a window, that is the extent of the scene which we want to display, and then we want to make a sort of a answer to a question whether a particular primitive is inside the window or not before we decide to display it, right. So, we for instance, we looked at the point clipping, right. So, point is the simplest primitive. So, we wanted to answer this question whether a particular point is inside the window or it is outside the window, right. So, for the purpose of simplicity, if I consider a window of, let us say, a rectangular window, then this question can easily be answered by just looking at the coordinates of the point and the extent of the window to decide whether a particular point is inside or outside, right. So, here P is the point which is outside the window, or Q is the point which is inside the window, right. So, a simple comparison gives us that result. And then we also looked at the possibility of extending this idea of clipping a point to a line just applying at the end points of the line, right. And we figured out that it was not always possible that we could determine whether a line is inside or outside just by looking at the two end points, right. And in this respect, we had a clipping algorithm suggested by Cohen and Sutherland, right, where the idea was that you are given a window, right, which is shown here as a gray region, and you want to decide things which are inside that window. So, what you do is you basically give a bit code to this window and the neighboring regions this window has, right. So, then we can actually devise a scheme by which we can decide for some trivial cases, right. So, this process basically is doing that given one boundary of the window, I can decide whether the line is on this side of the window edge or the other side of the window edge, right. So, in case if it is on the other side, which is actually the side where the window exists, I would declare that it is possibly visible, right. So, just by looking at then the bit code which I get for the end points of the line, right, I can decide whether I need to trivially reject the line or accept the line, right. So, if the two end points are inside the window, then the bit code for the two end points is going to be 0 0 0 0, right. And then I can basically follow some other some logical operation which we figured out was like taking an AND of the two end points, where if I take the AND of the two end points, then if I obtain non-zero bit, right, only exactly one bit on, then I can say that it is rejected, trivially rejected by this window, right. So, these are the cases which we can see are the cases for trivially acceptance and rejection, right. So, this line is trivially accepted because the two end points have 0 0 0 as the bit codes, and here the two end points are actually on this side. If you look at this edge of the window, they are on one side of the window edge, and if I take the logical end of the two end points, I find out that it is exactly 1, right. Therefore, I can trivially reject it, right. And however, if the cases are of this kind, right, where this trivial rejection criteria does not get satisfied, then I need to do some more work, right. So, these are the cases like where you have one end point on this side and one end point is actually inside the window, right, and I get a logical AND which is 0 for all the bits, then I need to find out the intersection point here with the window edge, so that I actually get the segments of the line which is inside and which is outside, right. So, I can subdivide that line again at the intersection point and again check for the trivial rejection and trivial acceptance, right. That is the idea. So, here are also the cases which are actually not visible from this window, right. The two endpoints are here and here, but they are potentially visible because of the not satisfying the trivial rejection criteria, right. So, we need to still work on to figure out the segments of the line and therefore, check for each of the segments for trivial rejection and acceptance, right. So, this was the coherent Sutherland algorithm. So, the properties of coherent Sutherland is basically a very simple algorithm, right, just checking for the endpoints, and it is still popular because most of the time when you do clipping, it is actually primarily against a rectangular region. Okay, that is a very natural choice for a window, right. So, this limitation of rectangular region may be all right for most of the practical applications. So, still it is popular, right, as a method, and the extension to 3D as we saw it last time is fairly straightforward, right. So, instead of having 4-bit opcode, we actually have 6-bit opcode, right, and basically we are comparing it with the faces of the parallelopiped structure, whether there is a line which is possibly can be trivially rejected or accepted, right. So, now let us try to see some other way of doing this clipping, where we can resolve certain limitations of this method. So, one of the limitations is that we are restricting this to a rectangular region, right. Maybe we can still design certain bit code for the two endpoints if we have a convex region. For instance, if I have a triangular region, maybe I can still do in a very similar fashion the way I did for a rectangular region, right, doing some kind of a logical operation for the two endpoints, but it might become a cumbersome even for a general convex polygon, right. So, there is another very popular clipping algorithm which is Cyrus-Beck line clipping algorithm, and in fact, there is a slight variation to it from Liang and Barsky. So, they are sort of equivalent, right, in terms of the way they work. So, this is applied with respect to any convex region as a window, right. So, you can take up any convex region, and we will see later on that it could also be possibly be extended for non-convex regions. Okay. So, what we do here is we consider a line in question which is to be clipped, right, as a parametric representation of a line, right. So, if I have a line A B, so I represent this line as L T equals to A plus B minus A times T, right, where T is the parameter which runs between 0 and 1. So, the range of 0 and 1 makes this line a finite line, right, between the two endpoints A and B, right. So, I have the representation of the line which is to be clipped as a parametric representation, fine. Now, as far as the window edge is concerned, right. So, what I am trying to see it as that window basically consists of several edges, right. So, I am trying to answer the question of clipping with respect to the window edges, right. So, I represent a window edge using an implicit representation, right. So, implicit representation basically means that I have a line L Q which is given as Q minus P dot n, right. So, it is actually giving me the answer to the question on which side of the line the point Q is, given the point P is on the line and n is the normal to the line which I consider as defining for the inside of the line or a particular side of the line, right. Something similar to what we also observed in line drawing algorithm, right, where we were trying to answer the question of the location of the midpoint with respect to the line, right. So, I have this implicit representation which actually enables me to answer the question on which side of the line the point Q lies, right. So, this P point is actually any point on the line, right. So, in other words, it is a sort of a signed distance of the point Q from the line, right, and the sign of that gives me whether it is this side or that side, right. So, now given the representation which I am going to use for the line to be clipped and for the window edges against which I am going to check for clipping in implicit form, let us see how we can go further for designing the clipping algorithm. So, what do we have here? We basically do an evaluation, right. We do an evaluation of a given point Q, which is nothing but through the equation of the line itself, and if we figure out that this point Q is greater than 0, right, then it is towards the inside half space of the line. So, I have this notion of defining the inside and outside, right. So, inside is the side where I have defined this normal n, right. So, this is again a similar kind of a representation for half space, right. So, just looking at the sign, what I have from this evaluation, if it is greater than 0, I have the point towards the inside half space of the line. If it is less than 0, it is on the outside of the half space of the line, and if it is equal to 0, then the point is actually on the line itself, right. So, now in fact, if you recall the way we were trying to design this trivial rejection and trivial acceptance, similarly in the case of Cohen and Sutherland, right, we can actually look at certain indications for trivial acceptance and trivial rejections from here, right. For instance, if I figure out that the point Q turns out to be inside with respect to all the edges of the window, then the point is going to be inside the window itself, right. And if it so happens that for the two end points of the line this is the case, right, then the line is inside the window, right. This is equivalent to the trivial acceptance of the Cohen-Sutherland algorithm, right. And similarly for the rejection, right, because we basically that bit code was just trying to do this inside outside operation with respect to the half space defined by the window edge. That is precisely it was doing, right. So, we can do it in this fashion as well, right. These are two basically equivalent as far as the computation goes, right.
How do we figure out if the line is inside the region just by looking at one edge of the window?
No, basically what we will do is we have, let us say, the with respect to one line we check, right, if the two end points happen to be outside that window edge, right, this is going to be rejected, right, fine. Okay. So, now let us try to see more in details about what I was trying to suggest is window edge. If I have given in implicit representation L q is equal to q minus p dot n, and the line segment given in parametric representation L t is equal to a plus t b minus a, then what I mean by saying trivial rejection is basically looking at the two endpoints of the line which are a and b, right. So, they should satisfy the criteria of being outside that line, right, and which is that it is negative, less than 0, right. Both of them give me this negative, right. Similarly, for the trivial acceptance, right. So, this basically answers your question, right.
Actually, I just wanted to clarify that in reject we just have to consider it outside any one of the edges,
That is right.
whereas in accept we needed it to be inside all of the edges.
That is correct. That is correct. So, I will not be able to declare the line as such inside unless I have gone through all the window edges, right. Okay. So, now we have basically looked at the cases of this nature. So, we are basically right now addressing the question of with respect to one window edge. So, this inside outside notion is actually associated to an edge, right, and then we can run through with respect to all the edges, and then that is where we will get the algorithm design. So, here this case we have resolved, this case also we have resolved, right, and obviously there will be situations like this and one requires more work to do. Right. Similarly, what happened in the case of Cohen-Sutherland, right. Now, let us try to see with the given representations we have, can we have these things in a sort of concise way. So, when I say that I have this line a b in a parametric representation, L t is equal to a plus b minus t, and the window edge in the implicit form, then finding this intersection, right. Now, we are talking about the more work which we need to do when a line intersects the particular window edge, right, which basically requires you to find out this point of intersection, and that you can find out by just substituting this L t, right, into the implicit equation you have, right, and solve for t, right. So, it becomes very simple solution, right. So, that is what I have done. I basically substituted here L t, this is and then after just rearranging these terms, I can figure out this equation a minus p dot n plus t b minus a dot n equals to 0. All I need to do is get this t, right, and of course, the t has to be within the range 0 and 1, right. Okay. So, just to give you the whole picture. So, I have it this t determined as a minus p dot n divided by a minus b dot n, right, which I can further write like this, right. So, remember that when we were trying to address the question of these, right, L a less than 0, L a greater than 0, right, and now we are basically looking at these a minus b dot n, which is nothing but that is the same computation we did. See, L a greater than 0 meant what? Substituting a into my implicit equation of q minus p dot n, right. So, as far as the computational aspect is concerned, it was exactly this, right. So, what I am trying to say is that the computation which I did for deciding my trivial acceptance and trivial rejection cases, I just have to reuse them. I do not have to recompute these, right. I just have to reuse them. So, that is an advantage I have, right. So, now once I have done this, then it is basically a matter of doing this with respect to all the edges, right. What will happen is that I can then redefine my A's and B's according to what I get as a point of intersection and give that to the succeeding edge, the next edge, right. All I need to do is redefine these endpoints and go through the entire cycle of my edges I have, right, and at the end of it I am done. Right. And clearly, when you look at this, this does not restrict you to the form of the window I have. Only condition I have is that the window needs to be convex, does not matter what shape I have, right. So, it does not really restrict it to rectangular shape of the window. I can apply this to any convex shape. Okay. Now, there is a small variation what I just said, that let us say instead of doing this evaluation of T and then updating my endpoints A and B and then give it to the next window edge, let us say I try to find out the point of intersection with respect to all the window edges. So, that is where these two are slightly different, Syrus-Beck and Lang, right. So, here what I am trying to suggest is that given a line AB, right, I have possibly 4 intersections with respect to, let us say I have a rectangular window with respect to each edge of the window, right. Now, the question which is being asked is that I find out these point of intersection, right, basically the T which gives me the point of intersection, right. Then can I figure out anything from those T to be able to decide what segment of the line is inside, if at all the line is inside the window, right. You understood what I am trying to suggest here? I am basically saying that okay, here is a line and you have these window edges. What I am trying to do is find out the point of intersection, possible point of intersection of this line with respect to the window edges, which are 4 in this case, right. And just looking at the values of T which I obtain, can I suggest anything for the acceptance or rejection of the segment of the line which could possibly be displayed within the window, right. Okay. So, basically let us say if I have these 4 point of intersection, then I am trying to answer which of these T I need to be able to label that this portion is inside the window, right. Okay. So, what I do is, let us say I have these T's which are computed as we have seen in this fashion, right. So, I have just actually swapped this A minus B to B minus A and put a negative sign in front, right. It is exactly the same thing. It just gives you a sort of a notion of direction. If I give for A T equals to 0 and for B T is equal to 1, right. So, it is all sending all it is suggesting that I am going from A to B, right. Now, let us try to evaluate this denominator term which I have here, B minus A dot n, which I call it as D, right. Now, just look at the sign of this, right. So, if the sign of this D is positive, that means d is greater than 0, then I label the t which I have computed as something like a T e. So, E here is referring to entering, right. So, the idea here is that if I have a line like this going from A to B and this is my normal, right, then it is in some sense saying that it is entering that edge or it is entering that space, right. So, I label these t's as T e, which I find for d greater than 0. Similarly, I have t for which the d is negative, right, less than 0, then I label this t as T L, and here L referring to leaving, right. So, here is the situation which I am trying to illustrate. Here you have this edge, right. So, this is the inside region for this edge, right, and when I find out this point of intersection here, so the T referring to this I label it as T L, because here when I look at this line, it is in some sense leaving that region, right. So, I have this notion of entering and leaving, which I use for labeling the different t's I obtain, right. Now, let us say if I can exploit this notion in order to decide which t's to select, right. Any suggestions you want to give? So, let us say if I consider this particular line, right, and you know what portion of the line is actually inside the window, right, and you now by now you know what t's will have the label E, right. These two t's are going to have T e and these two t's are going to have T l, right. So, is there anything you can think of which can give me this as the segment to be clipped, right, exactly. So, if I take the maximum of the T e's and the minimum of the T l's, I am okay, right. So, just this is what I said here, right. So, this T and this T, these are the T's which are of interest to be able to segment this line, right, which is to be clipped. So, the T of interest is the largest T e, which I can call it as T e max, right, and smallest T l, which I call it as T min l, right. So, now in fact, this can also help me further. Since I am just doing this evaluation of intersection points, right, and then I also need to decide whether the line is actually inside or outside, right. This can even help me doing this, where this T e max is greater than T l min, right. If this happens, then I reject the line, and that is what is happening in this case, right. Because see, this is what you will get as T max, right, and this is your T l min. So, you will just reject that line, right. So, the evaluation of this T e max and T L min can also help you for rejecting the line, right. So, this is basically based on finding out the intersection, that is all it is about, right. And the let us say the trivial rejection part comes as after the evaluation of these T's, right. So, now clearly as we have said that there is no restriction to the shape except that the shape needs to be convex, right. So, here there is an example where I have taken a convex window, right, which has got 8 edges, and P 1 P 2 is the line in question, and I can actually in a very similar fashion as I did for the rectangular region, I can do the clipping of this line and get these points, right. Now, the question is that if I give you a shape, so first of all you need to answer the question whether I can perform my clipping against that shape whatever I have given you, right. So, you need to answer the question whether the particular shape is convex or not. Right. So, how do you do that? Okay, let me just give you a very simple way of doing it. So, what you do is actually you look at the cross product of the adjacent edges, right. So, here in this case when I take a cross product of E 1 and E 2, and let us say my convention is that the thing which is coming out of this plane is positive, right. Then I say E 1 cross E 2 is positive, right, and so on. So, if I just take the cross product of all the adjacent edges, pair of edges, right. So, it turns out that in this case they are all going to be positive, or if I had chosen a different convention they could have been all negative, right. So, basically what we are saying is that if I find out that the cross product of the adjacent edges has the same sign, right, then I declare that polygon as convex. Is it fine? Now, let us try to take a shape which is non-convex and see that this gets violated, right. So, here is a non-convex shape. So, clearly that is what where you find the non-convexity, right, at this point V 4. So, what will happen is that you observe that there is a change of sign at some point. All these cross products do not give you the same sign. Then you say that the shape is non-convex, right. Now, the question is, can we still do clipping for a non-convex polygon or window? Yeah, let us say some sort of an extension of this method.
Here what prevented us was that we just took the extreme P's, whereas in the case of non-convex we will have to consider them as segments, say ranges of P's which might lie inside the.
Okay, no, see, let us say I do not want to change my algorithm as such, right. So, the question which is being basically asked, can I map the problem of solving for non-convex to convex by doing something, some sort of a pre-processing. So, the first observation could be that if I generate convex polygons out of it, right, that is one way to look at it, right, and then I actually do this clipping with respect to all the decomposed convex polygons, right. But often what happens is that when we are given such a polygon, such a non-convex polygon, the non-convexity arises only at, let us say, a few points, maybe one, right. So, maybe what we can do is we can do some correction to that non-convexity and still apply the algorithm which is for convex and arrive at our solution, right. So, here is with respect to this particular polygon, let us say what we can perhaps do is something like this. Let us say what I do is I make this polygon convex, right. So, making convex a polygon would actually may involve is finding out the convex hull of the points, right. In this situation, maybe it is just a matter of finding out where the change of sign occurred, right, and then I take the two end points which were adjacent to it and join by line and make that polygon as convex. But the situation could not be that simple, and you may actually require to find out a convex hull, right. So, you understand what a convex hull is? Okay, let me just give you a notional example, and we are not really, let us say, at the moment concerned for the exact algorithm of finding out a convex hull. So, what we have set of points, right, we are given set of points, just consider actually these set of points are nothing but nails, right, nails on a floor, right. You take a thread, start from a nail, right, and just wrap it around, right. Then what you see is whatever is given by that thread gives you the convex hull, right. So, let us say in such cases where we are interested in applying this clipping, we are able to figure out the convex equivalent without going through an elaborate algorithm of convex hull, right. So, we figure out, let us say, as I said in this case, just by looking at the adjacent points to the point which had given the different sign, and I join this line and I get a convex polygon, right. Then what I am trying to do here is, for the line which was given to me as P1 P2, right, that is the line in question which was to be clipped, I first find out the line which is clipped against this polygon, right, the new polygon, including this blue line, right. So, I basically get the points P3 and P4, right. Now, what I can do is, then I consider this polygon which was sort of the additional polygon for making the other polygon convex, right. Then I do a clipping against this polygon, right, for the resulting line I obtained, right, which was from P3 P4, and I get the point P5, right. So, I just do a clipping of the line with respect to this polygon, right, and then I subtract this from what I had obtained earlier, right. So, at the end I obtain the line P3 P5, which is the resulting line to my interest, right. So, it is basically applying the same convex region algorithm and doing some pre-processing and post-processing to get the line clipped, right. There is another interesting aspect to it, is that when I say that this is the portion I had got, or the way we have seen the clipping algorithm, which actually gives you the line which is clipped against the polygon, which is inside the window, right. So, I may call that as something like an interior clipping, right. So, in fact, when I did interior clipping to find out P4, P5, I can do the exterior clipping, that means the line which is not inside, but outside that region, to give me P3, P4, right. So, I can just have interior clipping and exterior clipping, right. So, these are sort of useful when you have you seen this, let us say, the exterior clipping being applied somewhere? What happens to your window management system? You have a window management system, right. So, one window overlays the other window and so on and so forth, right. And what you see is actually the exterior clipped display from the window which is in front. Right. So, one can think that in terms of clipping, that is what I am trying to basically suggest, right. So, this basically covers line clipping, right, with respect to a polygon which is generally a convex, but even if it is non-convex, for simple non-convexity we can still apply a modified version of the same algorithm, right. So, you got to be ready for assignment. So, that is going to be a part of your first assignment, right. So, now next question which is to be asked is, let us move on to a more complex primitive, right. We started with point, then we went to line. Let us say I want to do polygon, right. So, I have a polygon as an input primitive. I want to do a clipping of this polygon against the window, right. So, the question which is here is, can I extend the line algorithm to do polygon clipping? And the answer is what? Yes, no, maybe? See, one thing which we have not talked about is that these polygons could also possibly be filled, right. They may have shade, they may have color. So, maybe then there might be some trouble. Okay. So, so that is what we are going to do next time, which is polygon clipping, right. So, given a polygon as an input primitive, how do we clip that against a window? So, once again, when we talked about this Cyrus-Beck and Lang-Barsky algorithm, line algorithm, just the way we had seen the extension to 3D in the case of Cohen and Sutherland, right. Here also it is straightforward, right. Yes or no? So, there in see, here we have considered window edges, right, as the lines against which we are trying to find out the clipping. So, there we will have window planes, right. So, we have a volume given by this convex region, right, and each of the faces of that volume is going to be a plane, right. But the test which we are going to have will have exactly the same computation, because we are basically answering the question of inside outside or this side or that side, right. So, instead of saying that with respect to a line, we will say that with respect to the plane. So, again it is a matter of checking the sign of that computation, right. So, that can be applied even for 3D. So, 3D clipping is just a straightforward extension of what we have seen as 2D clipping, right. Non-convex regions in 3D could slightly be more difficult, making them convex, right. Okay, thank you.